Subscribe to the channel so you don't miss out on any of these videos. Have you ever wondered what lies beyond the boundaries of our galaxy? What colossal forces might be pulling us through the universe without us even noticing? There's something out there so massive, so powerful, that it's bending the motion of not just our galaxy, but thousands of others. It's called the Shapley Supercluster, and it's the single largest gravitational force near us in the known universe. Just think about that for a second, a structure so vast and dense that it's shaping the way entire galaxies move. What is it? How does it affect us? And what secrets could it hold about the universe itself? To understand the Shapley Supercluster, we first need to step back and grasp the scale of what we're dealing with. Most of us are familiar with our own Milky Way galaxy, a sprawling collection of hundreds of billions of stars, planets, gas, and dark matter. But the Milky Way is just one galaxy in a much larger neighborhood known as the Local Group. This group, in turn, is part of an even larger cluster of galaxies, the Virgo Cluster, which is just one component of the Laniakea Supercluster, a vast region of space containing over 100,000 galaxies. Yet even within the incomprehensible size of Laniakea, the Shapley Supercluster stands out. Located about 650 million light-years from Earth, it contains over 8,000 galaxies and is estimated to be more than 10 million billion times the mass of our Sun. To put it simply, this is a structure so enormous that it defies the limits of human imagination. Its gravitational pull is so intense that it's affecting the motion of our entire supercluster, including the Milky Way itself. But here's where things get really mind-blowing. The Shapley Supercluster isn't just a collection of galaxies. It's a dense concentration of matter that includes not only visible galaxies but also vast amounts of dark matter, an invisible and mysterious substance that makes up about 85% of the universe's total mass. Dark matter doesn't emit, absorb, or reflect light, so we can't see it directly, but its gravitational effects are unmistakable. It's what gives the Shapley Supercluster its immense gravitational force, tugging on everything around it like a cosmic anchor. So, how does this affect us here in the Milky Way? Well, to understand that, we need to talk about something called peculiar velocity. Galaxies don't just drift through space randomly. They're influenced by the gravitational pull of massive structures like the Shapley Supercluster. In the case of our galaxy, we're not just orbiting within the Local Group or being pulled toward the center of the Virgo Cluster. We're also being dragged towards something called the Great Attractor, a mysterious region of space that lies in the same direction as the Shapley Supercluster. Scientists believe that much of the Great Attractor's pull can be attributed to the sheer mass of the Shapley Supercluster. In other words, the Shapley Supercluster isn't just a passive background feature of the universe. It's actively shaping the motion of galaxies millions of light-years away, including our own. It's like being caught in the current of a massive river, unable to escape the flow even though the source of the pull is far beyond what we can see with the naked eye. But there's still so much we don't understand. For example, how did the Shapley Supercluster form in the first place? To answer that, we have to go back to the early universe, just after the Big Bang. In its infancy, the universe was a nearly uniform soup of particles and energy, but tiny variations in density eventually grew into the massive structures we see today. Over billions of years, these regions of higher density began to pull in more and more matter, forming galaxies, clusters, and eventually superclusters like Shapley. Yet the Shapley Supercluster is an outlier even among superclusters. Its density is far higher than what we'd expect from random variations alone, suggesting that there may be additional factors at play. Could it be the result of a unique set of cosmic conditions? Or perhaps the influence of dark matter is even stronger here than in other parts of the universe? These are questions that astronomers are still trying to answer. What's particularly intriguing is how the Shapley Supercluster fits into the larger structure of the universe. Recent studies have revealed that the universe is organized into a vast cosmic web, with galaxies and clusters arranged along filaments of dark matter that span hundreds of millions of light-years. The Shapley Supercluster sits at the intersection of several of these filaments, making it a key node in the cosmic web. This unique position could explain its immense mass and gravitational pull, as it's essentially a convergence point for matter from multiple directions. As we continue to study the Shapley Supercluster, we're also uncovering new clues about the nature of dark matter and dark energy. These two mysterious components make up 95% of the universe, yet we know so little about them. The Shapley Supercluster serves as a kind of cosmic laboratory, allowing scientists to study how these forces interact on the largest scales. For example, by observing the motion of galaxies within the supercluster, we can estimate the distribution of dark matter and refine our models of how it behaves. Similarly, the Shapley Supercluster provides a unique opportunity to study dark energy, the mysterious force that's driving the accelerated expansion of the universe. How does dark energy interact with such a massive structure? Could the Shapley Supercluster hold clues to its ultimate fate? The more we learn about the Shapley Supercluster, the more questions arise. Why is it so much denser than other superclusters? What role does it play in the evolution of the universe as a whole? And perhaps most intriguingly, what lies beyond it? The Shapley Supercluster represents just one corner of the observable universe. But what if there are even larger structures out there, hidden beyond the limits of our current technology? If we look at the vastness of the observable universe, it's humbling to think that the Shapley Supercluster is just a tiny fraction of what might be out there. The observable universe spans about 93 billion light-years in diameter, yet we're limited by the speed of light and the universe's expansion. Beyond the Shapley Supercluster, there could be even more massive and enigmatic structures that we cannot yet detect. These regions might hold answers to some of the most profound questions in cosmology, or they might pose entirely new mysteries. For now, though, the Shapley Supercluster remains one of the most significant gravitational forces within our reach, and studying it offers us a unique perspective on the dynamics of large-scale structures. For instance, one of the most fascinating aspects of the Shapley Supercluster is how it interacts with neighboring superclusters. The universe is not a static place. Galaxies, clusters, and superclusters are constantly moving, shifting, and evolving under the influence of gravity. The Shapley Supercluster's immense gravitational pull not only affects its own galaxies but also influences the motion of nearby superclusters, creating a complex web of interactions that scientists are just beginning to untangle. One particularly interesting discovery is how the Shapley Supercluster interacts with the so-called dipole repeller. This term refers to a region of space with relatively low density, where matter is less concentrated. While the Shapley Supercluster is pulling galaxies toward it, the dipole repeller seems to be pushing galaxies away. Together, these opposing forces create a dynamic flow of matter, shaping the movement of galaxies across hundreds of millions of light-years. Understanding this interplay is crucial for mapping the large-scale structure of the universe and revealing the forces that govern it. Another area of active research is the role of dark energy in shaping superclusters like Shapley. Dark energy, as you might know, is the mysterious force causing the accelerated expansion of the universe. But how does it interact with massive gravitational structures? Does it counteract their pull, or does it influence the distribution of matter within them? The Shapley Supercluster provides a unique testing ground for these questions because of its sheer size and density. By studying how galaxies within the supercluster move relative to each other, scientists can gain insights into how dark energy operates on different scales. Let's not forget that the Shapley Supercluster also serves as a window into galaxy formation and evolution. The galaxies within this supercluster are not evenly distributed. Some regions are densely packed with galaxies, while others are relatively sparse. These variations offer clues about how galaxies form and cluster together over billions of years. For example, scientists have observed that galaxy interactions, such as collisions and mergers, are more common in densely packed regions like the Shapley Supercluster. These interactions can trigger bursts of star formation, alter the shapes of galaxies, and even influence the growth of supermassive black holes at their centers. Speaking of black holes, the Shapley Supercluster is home to some of the most massive black holes ever observed. These cosmic giants are millions or even billions of times the mass of our Sun and play a crucial role in shaping the galaxies around them. By studying the behavior of these black holes, astronomers can learn more about their impact on galaxy evolution and the role they play in regulating star formation. Could the intense gravitational environment of the Shapley Supercluster also influence the growth of these black holes? That's another question scientists are eager to answer. The Shapley Supercluster isn't just a collection of galaxies, it's a time capsule. Because light takes time to travel, when we observe the Shapley Supercluster, we're seeing it as it was 650 million years ago. This means it offers a glimpse into the universe's past, providing valuable data about what the cosmos looked like during a crucial period in its history. By comparing the Shapley Supercluster to other superclusters at different distances, and therefore different points in time, scientists can piece together a timeline of how these massive structures form and evolve. But let's bring it back to us here in the Milky Way. The Shapley Supercluster might seem impossibly far away, but its influence reaches us nonetheless. Its gravitational pull, combined with that of other nearby structures like the Great Attractor and the Dipole Repeller, determines the large-scale motion of our galaxy. This motion, known as the peculiar velocity, is a key factor in understanding our place in the universe. Without the Shapley Supercluster, the motion of galaxies in our region would look very different, and so would the cosmic map we're so carefully constructing. Still, for all we've learned, the Shapley Supercluster remains shrouded in mystery. What lies at its core? How does its composition differ from other superclusters? Could it harbor unknown phenomena that challenge our understanding of physics? These questions remind us that the universe is far more complex and surprising than we can currently comprehend. And then there's the matter of what comes next. The universe is expanding, but on smaller scales, gravity still dominates. Over billions of years, will the galaxies in the Shapley Supercluster continue to merge and form even larger structures? Or will the accelerating expansion of the universe eventually pull them apart, isolating them in a cosmic void? These are questions that only future generations of astronomers will be able to answer, as they continue to study the interplay between gravity, dark matter, and dark energy. It's fascinating to think that a structure as massive and influential as the Shapley Supercluster could be just one of many. In fact, some scientists speculate that there could be even larger superclusters beyond the observable universe, exerting gravitational influence on everything we see. If that's true, then the Shapley Supercluster might be just the tip of the iceberg, a tantalizing clue about the true scale of the cosmos. The possibility of even larger structures existing beyond our observable universe is not just a wild conjecture, it's a profound implication of cosmological principles. According to the cosmological horizon, the limit of what we can observe is determined by the speed of light and the age of the universe. But that doesn't mean the universe ends where our observations do. Far beyond the Shapley Supercluster, there could be other massive conglomerations of galaxies, perhaps even larger than anything we can currently imagine. These unseen forces might influence our observable universe in subtle but detectable ways. Take, for instance, the concept of dark flow. This phenomenon refers to the unexplained motion of galaxy clusters that seem to be drawn toward a specific direction in space. Some scientists hypothesize that this motion could be caused by massive structures lying beyond the observable universe. Could the Shapley Supercluster be part of a larger gravitational chain, itself influenced by something far greater that we cannot yet perceive? If so, it raises profound questions about the true scale of cosmic structures and how they interact across unimaginable distances. Even within the observable universe, the Shapley Supercluster challenges our understanding of how such massive structures form. According to current models of cosmic evolution, superclusters like Shapley should have taken billions of years to come together. Yet, its size and density suggest that it formed relatively quickly, posing a mystery to astrophysicists. This anomaly has prompted researchers to revisit theories about the role of dark matter and cosmic filaments, the vast, thread-like structures that connect galaxies across the universe. Dark matter, the invisible substance that makes up about 27% of the universe, plays a crucial role in the formation of superclusters. It acts as a gravitational scaffold, pulling ordinary matter into dense regions where galaxies and clusters eventually form. The Shapley Supercluster's immense gravitational pull suggests it contains an extraordinary amount of dark matter. By studying the distribution of dark matter within Shapley, scientists hope to refine their models of how these mysterious particles influence the universe on both small and large scales. But there's another enigma hidden within the Shapley Supercluster: its sheer diversity. The galaxies within this region range from young, star-forming spirals to old, elliptical galaxies filled with ancient stars. This diversity offers a treasure trove of data for astronomers trying to understand the life cycles of galaxies. For instance, why do some galaxies within Shapley thrive with vigorous star formation, while others appear to have ceased producing new stars entirely? The answers to these questions could reveal much about the factors that drive galaxy evolution. Interestingly, the Shapley Supercluster also serves as a laboratory for studying galaxy cannibalism, a process in which larger galaxies consume smaller ones. This phenomenon is more common in densely packed regions like Shapley, where galaxies are close enough to interact gravitationally. When galaxies merge, their central black holes often combine as well, releasing enormous amounts of energy in the form of gravitational waves. Detecting these waves from events within the Shapley Supercluster could provide crucial insights into the nature of black holes and the dynamics of galaxy mergers. Let's not forget about the role of hot gas in the Shapley Supercluster. Observations with X-ray telescopes have revealed vast amounts of superheated gas filling the spaces between galaxies. This gas, which can reach temperatures of millions of degrees, emits X-rays that astronomers use to map the supercluster's structure. The distribution of this hot gas provides clues about the supercluster's gravitational landscape and helps scientists identify regions of higher density. But the presence of such hot gas also raises questions. What heats it to such extreme temperatures? Some theories suggest that it's the result of shocks from galaxy collisions, while others point to the influence of supermassive black holes. Whatever the cause, the study of this hot gas is vital for understanding the overall dynamics of the Shapley Supercluster. Another fascinating aspect of the Shapley Supercluster is its role in the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang. As light from the CMB passes through massive structures like Shapley, it can be altered in subtle ways, a phenomenon known as the Sunyaev-Zeldovich effect. By studying these distortions, scientists can measure the mass of the supercluster and gain insights into the distribution of matter in the universe. And yet, despite all we've learned, the Shapley Supercluster remains an incomplete puzzle. One of the biggest challenges in studying it is its distance from us. At 650 million light-years away, even the most advanced telescopes struggle to resolve its individual galaxies in detail. Moreover, the sheer scale of the supercluster makes it difficult to map comprehensively. Scientists rely on a combination of optical, X-ray, and radio observations to piece together its structure, but many questions remain unanswered. For instance, how did the Shapley Supercluster become so massive in the first place? Did it form through the gradual accumulation of smaller clusters, or was it the result of a more dramatic process? Some researchers suggest that the supercluster might have grown rapidly during a period of cosmic turbulence when dark matter and ordinary matter clumped together more efficiently. If true, this would challenge existing models of cosmic evolution and force us to rethink how large-scale structures form in the universe. The Shapley Supercluster also raises questions about the future of the universe. As the cosmos continues to expand, will superclusters like Shapley remain gravitationally bound, or will they eventually be torn apart by the accelerating expansion driven by dark energy? If the latter is true, then the Shapley Supercluster might represent a fleeting moment in cosmic history, a snapshot of a universe that was once more connected and dynamic. And what about its impact on the local group, the small collection of galaxies that includes the Milky Way? While the Shapley Supercluster is too far away to directly affect us, its gravitational influence contributes to the large-scale flow of galaxies in our region. This flow, in turn, shapes the environment in which our galaxy exists, influencing everything from star formation rates to the distribution of dark matter. Ultimately, the Shapley Supercluster is a testament to the complexity and beauty of the universe. It reminds us that even in the vast emptiness of space, there are regions of incredible richness and activity. By studying Shapley, we not only learn about the forces that shape the cosmos but also gain a deeper appreciation for our place within it. The Shapley Supercluster also serves as a gateway for understanding the intricate relationships between galaxies, clusters, and the underlying cosmic web. The cosmic web is a vast, interconnected structure of filaments made of dark matter, gas, and galaxies, forming a skeleton upon which the universe is built. Within this web, superclusters like Shapley act as nodes, massive concentrations of matter where filaments converge. By studying Shapley, scientists aim to uncover how these filaments channel galaxies and matter into such dense regions over billions of years. One intriguing feature of the Shapley Supercluster is its role in cosmic streams, vast flows of galaxies and galaxy clusters moving toward regions of higher density. Shapley is not an isolated structure but part of a larger network, influencing and being influenced by the surrounding cosmic environment. Observations suggest that neighboring galaxy clusters are being drawn into Shapley, adding to its already immense mass. This process demonstrates how gravitational forces shape the universe on grand scales, creating a dynamic interplay between clusters and superclusters. Additionally, Shapley offers a unique opportunity to study the effects of gravitational lensing, a phenomenon where light from distant objects is bent as it passes through the gravitational field of a massive object, like a supercluster. The Shapley Supercluster's immense mass makes it a powerful gravitational lens, distorting the light from background galaxies. By analyzing these distortions, astronomers can create detailed maps of the supercluster's mass distribution, including the elusive dark matter that dominates its structure. Gravitational lensing also allows scientists to peer deeper into the universe. The bending of light magnifies distant objects, making it possible to observe galaxies that would otherwise be too faint to detect. This effect has provided invaluable data about the early universe, helping researchers understand how galaxies formed and evolved over cosmic time. In this sense, the Shapley Supercluster acts as both a subject of study and a tool for exploring the universe's distant past. Despite its vast size and influence, the Shapley Supercluster is only one piece of a much larger puzzle. Astronomers have identified other massive superclusters, such as the Hercules and Coma superclusters, each with its own unique characteristics. Comparing these structures helps scientists uncover patterns and differences in how superclusters form and evolve. Shapley's extreme density and mass make it an outlier, challenging existing models and prompting researchers to refine their theories. Moreover, the study of the Shapley Supercluster has implications for understanding the mysterious force known as dark energy, which is driving the accelerated expansion of the universe. Dark energy works against gravity, pulling galaxies and clusters away from each other over time. However, in regions like Shapley, gravity dominates, creating pockets where dark energy's influence is temporarily countered. These regions provide a unique opportunity to study the interplay between gravity and dark energy, offering insights into the ultimate fate of the universe. Another layer of mystery surrounding the Shapley Supercluster lies in its star formation activity. Galaxies within dense clusters often experience starburst events, where star formation occurs at an accelerated rate. However, the intense gravitational interactions in regions like Shapley can also strip galaxies of their gas, the raw material needed to form stars, leading to a phenomenon known as galactic quenching. Understanding why some galaxies thrive while others wither in the same environment is a key question in modern astrophysics. This balance between creation and destruction extends to the supermassive black holes at the centers of galaxies within Shapley. These black holes influence their host galaxies and the surrounding environment through powerful jets of energy and radiation. The Shapley Supercluster provides a unique setting for studying these interactions on a grand scale, revealing how black holes shape the evolution of galaxies and clusters. Another captivating aspect of the Shapley Supercluster is its potential to test the limits of our current theories of physics. For example, the distribution of galaxies and matter within Shapley challenges the predictions of general relativity, Einstein's theory of gravity. While general relativity has been remarkably successful in describing the behavior of gravity on smaller scales, its application to massive structures like Shapley is less well understood. By analyzing the motions of galaxies and the bending of light within the supercluster, scientists can test whether general relativity holds true on these enormous scales or if modifications are needed. The Shapley Supercluster also prompts questions about the nature of cosmic voids, the vast, empty regions of space that surround superclusters and filaments. These voids are just as important as the structures themselves, providing a stark contrast that helps define the cosmic web. Studying the interaction between the dense regions of Shapley and the surrounding voids can reveal much about the large-scale distribution of matter in the universe. And then there's the role of Shapley in shaping the evolution of the Milky Way and the local group. While Shapley's direct gravitational pull on our galaxy is minimal due to its distance, its presence contributes to the overall gravitational landscape of the universe. This, in turn, influences the motion of the local group within the Laniakea supercluster, of which Shapley is a dominant feature. Understanding this connection helps place our galaxy within the broader context of cosmic structures. The story of the Shapley Supercluster is far from complete. As technology advances, new telescopes and instruments will allow scientists to study it in unprecedented detail. Upcoming projects like the James Webb Space Telescope and the Vera Rubin Observatory promise to uncover more about the galaxies within Shapley, their interactions, and their histories. These observations will provide critical data for unraveling the many mysteries that the supercluster presents. Ultimately, the Shapley Supercluster is a cosmic paradox, both a testament to the universe's immense scale and a reminder of how much we have yet to understand. Its study pushes the boundaries of human knowledge, inspiring awe and curiosity about the forces that shape our universe. As we continue to explore this massive structure, we are not just learning about the cosmos but also about our place within it. The Shapley Supercluster's influence on our understanding of the cosmos is as much philosophical as it is scientific. Its immense size and complexity force us to grapple with the sheer enormity of the universe. Structures like Shapley are not merely collections of galaxies. They are markers of the universe's evolution, bearing the imprints of billions of years of cosmic history. By studying Shapley, we're not only looking outward but also inward, contemplating humanity's role in the vast, interconnected tapestry of the cosmos. One of the most striking aspects of the Shapley Supercluster is its potential to reveal secrets about the mysterious early universe. The galaxies within Shapley are not uniform in age. Some are ancient, dating back to when the universe was only a few billion years old. These old galaxies act as time capsules, preserving clues about conditions in the early cosmos. By studying their composition, structure, and movement, astronomers can gain insights into how the first galaxies formed and how large-scale structures like superclusters emerged from initial density fluctuations in the primordial universe. This leads to questions about the role of dark matter in shaping the Shapley Supercluster. Dark matter, an invisible and enigmatic substance, is thought to make up about 85% of the universe's total mass. Without it, structures like Shapley would not exist. The gravity from dark matter is what allowed galaxies and clusters to come together and form such dense regions. Observations of the Shapley Supercluster provide some of the best evidence for the existence of dark matter. By mapping the motions of galaxies and the effects of gravitational lensing, scientists can infer the distribution of dark matter within Shapley, even though it cannot be directly observed. Dark matter's role in the cosmic web becomes even more intriguing when we consider the vast filaments that connect superclusters like Shapley. These filaments are believed to be composed primarily of dark matter, serving as highways for the flow of galaxies and gas. Shapley sits at a crossroads of these filaments, acting as a gravitational sink that draws material inward. This interconnectedness highlights the importance of understanding not just individual structures but the entire cosmic network. Another layer of mystery involves the chemical composition of galaxies within the Shapley Supercluster. The stars and interstellar gas in these galaxies contain elements that were forged in earlier generations of stars. By analyzing the light emitted by these galaxies, scientists can determine the abundance of different elements, such as hydrogen, helium, carbon, and heavier metals. This information sheds light on the processes of star formation, supernova explosions, and the recycling of matter within galaxies over billions of years. In addition to its chemical makeup, the dynamics of the Shapley Supercluster pose fascinating challenges. The galaxies within this massive structure are not static. They move in response to the gravitational forces exerted by the cluster's overall mass. These motions create complex patterns of interaction, including collisions between galaxies. Such collisions can trigger bursts of star formation, distort galactic shapes, and even lead to the merging of galaxies into larger systems. The Shapley Supercluster is a living laboratory for studying these processes on an extraordinary scale. Moreover, Shapley provides an excellent testing ground for studying magnetic fields in space. While often overlooked, magnetic fields play a crucial role in shaping the behavior of gas and charged particles within galaxies and clusters. Observing the effects of magnetic fields in a dense environment like Shapley can help scientists understand their influence on star formation, the motion of cosmic rays, and the structure of intergalactic plasma. As we delve deeper into the mysteries of Shapley, we must also consider its place in the broader context of cosmic acceleration. One of the most perplexing discoveries of modern astronomy is that the universe's expansion is speeding up, driven by the enigmatic force of dark energy. How does this accelerated expansion interact with massive structures like Shapley? While gravity dominates within the supercluster, dark energy's influence becomes apparent on larger scales, stretching the fabric of space itself. Understanding this interplay could hold the key to solving one of the greatest mysteries in cosmology. The Shapley Supercluster also has implications for the search for extraterrestrial life. While the supercluster's vast distances and extreme environments may seem inhospitable, the sheer number of galaxies it contains increases the likelihood of finding planets that could support life. Shapley is home to billions of stars, many of which may host planetary systems. By studying these galaxies, we may uncover clues about the prevalence of habitable worlds in the universe. Despite all we've learned, many questions about the Shapley Supercluster remain unanswered. For instance, how did such an enormous concentration of mass come to exist in the first place? Was its formation influenced by rare, high-density regions in the early universe, or did it arise through the gradual accumulation of matter over billions of years? Answering these questions requires a combination of observational data, theoretical modeling, and simulations. Technological advancements will play a crucial role in uncovering these mysteries. The next generation of telescopes, such as the Extremely Large Telescope, (ELT), and the Square Kilometre Array, (SK), will provide unprecedented views of the Shapley Supercluster. These instruments will allow astronomers to observe fainter galaxies, measure the motions of stars and gas with greater precision, and map the distribution of dark matter in more detail than ever before. At the same time, computer simulations are becoming increasingly sophisticated. Using powerful supercomputers, researchers can create detailed models of how superclusters like Shapley form and evolve. These simulations incorporate the effects of gravity, dark matter, dark energy, and the physics of galaxy formation, providing a virtual laboratory for testing different theories. In many ways, the Shapley Supercluster represents the ultimate challenge for our understanding of the universe. Its immense scale, intricate structure, and profound influence on its surroundings make it a cosmic enigma. As we continue to study this colossal supercluster, we are not just uncovering the secrets of one region of the universe, we are piecing together the story of the cosmos itself. The journey to understand the Shapley Supercluster is far from over, and each new discovery brings us closer to answering the fundamental questions of our existence. What is the universe made of? How did it come to be? And what is our place within it? The Shapley Supercluster stands as a beacon of knowledge, guiding us toward answers that may one day illuminate the deepest mysteries of the cosmos. The Shapley Supercluster is not just a physical structure, it is a vast archive of cosmic history that demands our attention and invites questions about the very fabric of the universe. To truly understand its significance, we must explore how its existence challenges and refines some of the most fundamental theories in modern astrophysics and cosmology. One of the most profound implications of the Shapley Supercluster lies in its relationship with the cosmic web, the vast network of interconnected galaxies, filaments, and voids that make up the large-scale structure of the universe. The Shapley Supercluster, with its immense gravitational pull, is a focal point in this web, sitting at the intersection of multiple filaments. These filaments act like cosmic highways, channeling galaxies, dark matter, and gas toward the supercluster. Understanding how these filaments feed into Shapley provides critical insights into the mechanisms that drive the evolution of the cosmic web itself. These filaments are not just channels of matter but also pathways for energy and momentum transfer across the universe. The flow of material along these filaments toward Shapley is driven by gravity, but it is also influenced by the interplay between baryonic matter, the ordinary matter that makes up stars and galaxies, and dark matter. The behavior of gas within these filaments, its temperature, density, and ionization state, can reveal how matter collapses into dense regions like Shapley, shedding light on the processes that led to the formation of the first superclusters in the universe. The Shapley Supercluster also provides a unique laboratory for studying galactic interactions on a grand scale. Within such a dense environment, galaxies frequently encounter one another, leading to gravitational interactions that can reshape their structure and even merge them into larger systems. These interactions play a crucial role in the evolution of galaxies, influencing their star formation rates, triggering bursts of activity in their central supermassive black holes, and altering their morphology. For instance, spiral galaxies within the Shapley Supercluster may lose their distinctive arms and transform into elliptical galaxies due to repeated interactions with neighboring galaxies. These galactic collisions and mergers often lead to the formation of giant elliptical galaxies, which are among the most massive and luminous galaxies in the universe. Shapley is home to several of these behemoths, whose formation histories are deeply intertwined with the supercluster's overall evolution. By studying these galaxies, astronomers can gain insights into the end stages of galactic evolution and the processes that shape the most massive structures in the universe. Another intriguing aspect of the Shapley Supercluster is its role as a hotspot for star formation. While dense environments like Shapley are typically thought to suppress star formation due to the high temperatures and pressures within galaxy clusters, certain regions within the supercluster exhibit intense bursts of star-forming activity. This paradox challenges conventional models of star formation and raises questions about the conditions that allow stars to form in such extreme environments. The intergalactic medium, IgM, within the Shapley Supercluster is another area of active research. The IgM, which consists of diffuse gas that fills the space between galaxies, is a crucial component of the cosmic ecosystem. In Shapley, the IgM is heated to extreme temperatures by gravitational compression and shock waves generated during galactic collisions. Studying this hot gas can provide valuable information about the thermodynamic processes at work within the supercluster, as well as the enrichment of the IgM with heavy elements produced by stars and supernovae. These heavy elements, often referred to as metals in astrophysical terminology, are ejected into the IgM through galactic winds and outflows driven by star formation and black hole activity. By analyzing the chemical composition of the IgM in Shapley, astronomers can trace the history of metal production and distribution within the supercluster, offering a glimpse into the life cycles of galaxies and the stars within them. The Shapley Supercluster also offers a unique perspective on the enigmatic phenomenon of cosmic acceleration. The accelerated expansion of the universe, driven by dark energy, has profound implications for the formation and evolution of large-scale structures like Shapley. While gravity acts to pull matter together and form dense regions, dark energy counteracts this process by stretching the fabric of space. The balance between these opposing forces determines the ultimate fate of structures like Shapley and provides a testing ground for theories about the nature of dark energy. One of the most fascinating tools for studying the Shapley Supercluster is the phenomenon of gravitational lensing. This occurs when the immense gravitational field of the supercluster bends the path of light from more distant objects, magnifying and distorting their appearance. Gravitational lensing not only provides a way to map the distribution of dark matter within Shapley but also allows astronomers to study faint, distant galaxies that would otherwise be too faint to observe. The interplay between light and gravity within Shapley also has implications for our understanding of cosmic time scales. Because light takes millions or even billions of years to travel from distant galaxies to Earth, observing Shapley is like looking back in time. The light we see from galaxies within the supercluster represents their appearance at different stages of their evolution, allowing astronomers to piece together a timeline of events that have shaped the structure over billions of years. The study of the Shapley Supercluster also raises profound philosophical questions about the nature of cosmic structure and order. How do such massive and intricate systems arise from the seemingly chaotic initial conditions of the Big Bang? What role do fundamental forces and universal constants play in shaping the universe on such grand scales? These questions not only deepen our scientific understanding but also challenge us to think about the underlying principles that govern the cosmos. The Shapley Supercluster reminds us of the interconnectedness of the universe. Its influence extends far beyond its immediate vicinity, affecting the motion of our own galaxy and contributing to the complex web of interactions that define the cosmos. By studying Shapley, we are not just learning about one supercluster, we are uncovering the story of the universe itself, piece by piece. As technology continues to advance and our observational capabilities improve, the mysteries of the Shapley Supercluster will gradually come into focus. Yet, with each new discovery, new questions will inevitably arise, ensuring that this colossal structure will remain a source of fascination and inspiration for generations to come. The Shapley Supercluster's sheer size and gravitational power not only influence our cosmic neighborhood but also serve as a vital probe into the hidden components of the universe, such as dark matter and dark energy. While visible galaxies and gas account for a portion of the mass within Shapley, the majority of its gravitational pull arises from dark matter, an enigmatic substance that does not emit, absorb, or reflect light. By examining the movement of galaxies and the properties of gravitational lensing within Shapley, astronomers can infer the distribution of this invisible matter, offering clues about its nature and role in the universe. Dark matter serves as the scaffolding for the formation of large-scale structures like Shapley, and its gravitational influence dictates the clustering of galaxies within the supercluster. However, its exact composition remains one of the greatest unsolved mysteries of modern physics. Is it made of undiscovered particles? Could it be explained by modifications to our understanding of gravity? The Shapley Supercluster, with its enormous concentration of mass, provides a natural laboratory to test these competing theories and push the boundaries of our knowledge. Equally compelling is the role of dark energy in shaping the Shapley Supercluster. While gravity works to pull matter together into dense regions like Shapley, dark energy exerts a repulsive force, driving the accelerated expansion of the universe. This cosmic tug-of-war shapes the fate of structures like Shapley and raises profound questions about the ultimate destiny of the universe. Will gravity eventually overcome dark energy and cause the universe to collapse back on itself? Or will dark energy dominate, causing the universe to expand forever? The Shapley Supercluster is particularly important for testing these scenarios because of its position in the cosmic web and its influence on surrounding structures. By studying how the supercluster evolves over time, astronomers can refine models of cosmic evolution and better understand the interplay between dark matter, dark energy, and ordinary matter. Another fascinating aspect of the Shapley Supercluster is its ability to reveal the dynamics of galaxy clusters on unprecedented scales. Within the supercluster, individual clusters of galaxies orbit each other in a complex gravitational dance, influenced by the overall gravitational potential of the structure. These interactions lead to the formation of massive shock waves, which heat the intergalactic gas to millions of degrees and generate powerful emissions in the X-ray and radio wavelengths. The properties of this hot gas provide critical insights into the thermodynamics of the supercluster. For example, the temperature and density of the gas can reveal the energy released during galaxy cluster mergers, while the presence of magnetic fields and relativistic particles can shed light on the processes that generate cosmic rays. These high-energy particles, which travel at nearly the speed of light, are thought to be accelerated by shocks and turbulence within the supercluster, making Shapley a key site for understanding their origins. In addition to its physical properties, the Shapley Supercluster offers a window into the chemical evolution of the universe. The heavy elements found in the intergalactic medium within Shapley were forged in the cores of stars and distributed throughout the supercluster by supernova explosions and galactic winds. By analyzing the chemical composition of this gas, astronomers can reconstruct the history of star formation and chemical enrichment within the supercluster, tracing the life cycles of stars and galaxies over billions of years. The study of the Shapley Supercluster also intersects with the field of cosmic magnetism, an area of research that seeks to understand the origin and role of magnetic fields in the universe. Observations of polarized radio waves from galaxies and quasars within and around Shapley revealed the presence of large-scale magnetic fields that permeate the supercluster. These fields, which are thought to be amplified by turbulent motions in the gas, play a crucial role in shaping the behavior of charged particles and influencing the dynamics of the intergalactic medium. Despite its enormous size and complexity, the Shapley Supercluster is just one piece of a larger cosmic puzzle. It is part of a network of superclusters and voids that make up the large-scale structure of the universe, a structure that is thought to have formed from tiny fluctuations in the density of matter shortly after the Big Bang. The study of these structures provides a direct link between the earliest moments of the universe and its present state, allowing astronomers to test theories of cosmic inflation, the rapid expansion of the universe in its first fractions of a second. The Shapley Supercluster also plays a key role in the search for the cosmic flow, the large-scale motion of galaxies driven by gravitational forces. The motion of our galaxy, the Milky Way, toward the Shapley Supercluster is part of a broader pattern of motion that includes other massive structures like the Great Attractor and the Dipole Repeller. By mapping these motions, astronomers can gain a deeper understanding of the distribution of mass in the universe and the forces that shape its evolution. One of the most intriguing questions raised by the Shapley Supercluster is whether similar structures exist elsewhere in the universe. Are there other regions of comparable size and density that exert a similar influence on their surroundings? If so, what can these structures tell us about the distribution of matter and energy on the largest scales? The discovery of such structures would provide valuable context for understanding the uniqueness of Shapley and its role in the cosmic web. The Shapley Supercluster also has profound implications for the search for extraterrestrial life. Within its vast expanse are billions of galaxies, each containing billions of stars and potentially trillions of planets. The diversity of environments within Shapley, from dense galaxy clusters to more isolated regions, provides a wide range of conditions for the potential emergence of life. By studying the properties of these environments, astronomers can refine models of habitability and better understand the factors that contribute to the development of life on other worlds. As our observational capabilities continue to improve, the mysteries of the Shapley Supercluster will only deepen. New telescopes and instruments, such as the James Webb Space Telescope and next-generation X-ray observatories, will provide unprecedented views of this colossal structure, allowing astronomers to probe its properties in greater detail than ever before. These observations will not only advance our understanding of Shapley but also contribute to broader efforts to map the universe and unravel its most profound mysteries. The Shapley Supercluster is more than just a collection of galaxies. It is a testament to the power of gravity, the complexity of the cosmos, and the enduring human quest to understand our place in the universe. By studying this immense structure, we are not only exploring the universe on its grandest scales but also deepening our appreciation for the intricate and interconnected nature of the cosmos. The Shapley Supercluster stands as a pinnacle of cosmic discovery, but to truly grasp its significance, we must delve deeper into its role within the cosmic web. The universe is not randomly distributed. It resembles an intricate three-dimensional network of filaments, voids, and dense nodes. Superclusters like Shapley form the nodes where filaments converge, creating hubs of galactic and intergalactic activity. These filaments, composed of gas, dark matter, and galaxies, channel material towards superclusters, feeding their growth over billions of years. The Shapley Supercluster is one of the densest nodes in this web, and its gravitational influence extends far beyond its immediate boundaries. Scientists use sophisticated simulations and observations to model the flow of matter along these filaments, revealing how galaxies and gas streams are funneled into Shapley. These studies not only provide insights into the supercluster's formation but also enhance our understanding of the larger cosmic architecture. One particularly fascinating aspect of the cosmic web is how it acts as a bridge between the observable universe and the theoretical underpinnings of cosmology. The distribution of matter within the web reflects the conditions of the early universe, offering a direct test of theories about cosmic inflation and the nature of dark matter. The Shapley Supercluster, as one of the most prominent features of this web, serves as a crucial benchmark for these theories, helping to refine models of the universe's evolution from its infancy to its current state. Moving from the theoretical to the observable, the Shapley Supercluster is also a hotspot for galaxy evolution research. Within its dense environment, galaxies experience frequent interactions and mergers, leading to dramatic transformations in their structure and behavior. For instance, spiral galaxies, like our Milky Way, can be reshaped into elliptical galaxies through collisions, while the intense gravitational forces within Shapley can strip galaxies of their gas, halting star formation and leading to a phenomenon known as galaxy quenching. These processes are not only fascinating in their own right but also have profound implications for the broader field of astrophysics. By studying the galaxies within Shapley, astronomers can trace the life cycle of galaxies and uncover the factors that drive their evolution. This, in turn, sheds light on the history of our own galaxy and its potential future trajectory. The Shapley Supercluster is also a treasure trove for the study of active galactic nuclei, AGN, the extremely bright centers of some galaxies powered by supermassive black holes. The dense environment of Shapley provides ideal conditions for fueling these black holes, as frequent galaxy interactions channel gas toward their centers. Observations of AGN within Shapley reveal how these energetic phenomena influence their host galaxies and the surrounding intergalactic medium, shaping the evolution of the supercluster as a whole. One of the most exciting frontiers in the study of the Shapley Supercluster is its potential to reveal new physics. For example, discrepancies between the observed and predicted motions of galaxies within Shapley could point to the existence of previously unknown forms of matter or energy. Similarly, the distribution of galaxies and dark matter within the supercluster provides a natural testbed for alternative theories of gravity, challenging the conventional framework of Einstein's general relativity. The influence of the Shapley Supercluster is not confined to its immediate surroundings. Its gravitational pull contributes to the large-scale motion of galaxies across vast cosmic distances, a phenomenon known as the Shapley attractor. This motion is superimposed on the overall expansion of the universe, creating a complex pattern of galaxy velocities that can be measured through redshift surveys. These surveys, which map the distribution and motion of galaxies in 3 dimensions, are among the most powerful tools in modern cosmology, and the Shapley Supercluster plays a central role in their interpretation. In addition to its scientific significance, the Shapley Supercluster holds a special place in the history of astronomy. Its discovery and subsequent study represent a triumph of human ingenuity and perseverance, showcasing the power of observational astronomy to reveal the hidden structure of the cosmos. The techniques developed to study Shapley have paved the way for new discoveries, from the identification of other superclusters to the exploration of the most distant reaches of the universe. Despite all that we have learned about the Shapley Supercluster, many questions remain unanswered. For instance, what is the ultimate fate of this colossal structure? Current models suggest that, over billions of years, the galaxies within Shapley will continue to merge, forming an even larger and more massive cluster. However, the influence of dark energy complicates this picture, raising the possibility that the expansion of the universe could eventually pull the supercluster apart. The Shapley Supercluster also challenges us to think about the limits of human knowledge. Its immense scale and complexity remind us of how much we have yet to learn about the universe, from the nature of dark matter and dark energy to the processes that drive galaxy evolution. At the same time, it inspires a sense of wonder and curiosity, encouraging us to continue exploring the cosmos in search of answers. As we look to the future, the study of the Shapley Supercluster will undoubtedly benefit from advances in technology and methodology. Upcoming telescopes and observatories, such as the Vera C. Rubin Observatory and the Square Kilometre Array, will provide unprecedented data on the structure and dynamics of Shapley, allowing astronomers to probe its mysteries in even greater detail. Meanwhile, theoretical developments in fields like particle physics and cosmology will continue to refine our understanding of the supercluster's place in the universe. The Shapley Supercluster is more than just a scientific curiosity. It is a symbol of the interconnectedness of the universe and the intricate web of forces that govern its evolution. By studying this extraordinary structure, we gain not only a deeper understanding of the cosmos but also a greater appreciation for our own place within it. The Shapley Supercluster's enormity and its far-reaching gravitational influence provide an unparalleled opportunity to probe the deep questions surrounding the origins, evolution, and ultimate fate of the universe. However, as profound as our understanding of this supercluster may seem, the enigmatic details that surround it push the boundaries of our knowledge even further. To explore the Shapley Supercluster is to embark on a journey to uncover the very threads of the cosmic web that tie the universe together, influencing not just distant galaxies but also our own. One of the most compelling aspects of the Shapley Supercluster is its role in shaping the observable universe. While we often perceive the universe as an infinite expanse filled with countless galaxies, the reality is far more structured. This supercluster represents one of the most massive and concentrated regions within the observable universe, acting almost like a gravitational linchpin in the cosmic web. Such structures challenge us to rethink what we know about the limits of gravitational interactions on cosmic scales and the processes that govern galaxy clustering. To grasp just how this titanic superstructure forms and influences the cosmos, we must first return to its origins in the early universe. Shortly after the Big Bang, the universe was a nearly uniform soup of particles and energy, with tiny fluctuations in density seeded by quantum processes during the inflationary period. Over billions of years, these slight irregularities grew under the influence of gravity, forming the first stars, galaxies, and ultimately superclusters like Shapley. The very existence of this massive entity provides a direct link to the conditions of the primordial universe, allowing us to rewind the cosmic clock and study the forces that shape the universe's structure. Yet, despite its titanic gravitational dominance, the Shapley Supercluster is not simply an isolated phenomenon. Instead, it serves as a nexus in a larger, interconnected system of superclusters and voids. Researchers studying the motion of galaxies around the supercluster have revealed a fascinating interplay between Shapley and neighboring gravitational centers, such as the Great Attractor, a mysterious region of gravitational pull closer to the Milky Way. Together, these gravitational hubs create a dynamic cosmic dance, influencing the paths of galaxies and clusters across hundreds of millions of light-years. The Shapley Supercluster also provides a crucial testing ground for our understanding of dark matter and dark energy. These two elusive components of the universe remain among the greatest mysteries in modern science, and Shapley's immense scale amplifies their effects, making them easier to study. Dark matter, which does not emit or absorb light but interacts gravitationally, is thought to form the scaffolding upon which the supercluster's galaxies are arranged. Meanwhile, dark energy, the mysterious force driving the accelerated expansion of the universe, competes with gravity on cosmic scales, influencing the long-term stability of structures like Shapley. Through detailed observations of the Shapley Supercluster, scientists are beginning to unravel the balance between these two forces. For example, the distribution of galaxies and gas within the supercluster offers clues about the nature of dark matter, including whether it behaves like a particle, a wave, or something entirely different. At the same time, the large-scale motions of galaxies around Shapley provide indirect evidence for the influence of dark energy, helping to refine models of its behavior over time. Another key area of research involves the cosmic microwave background (CMB), the faint afterglow of the Big Bang that permeates the universe. When light from the CMB passes through massive structures like the Shapley Supercluster, it interacts with the gas and dark matter within, creating subtle distortions known as the Sunyaev-Zeldovich (SZ) effect. By studying these distortions, astronomers can measure the temperature and density of the supercluster's hot gas, providing valuable information about its composition and history. The gravitational lensing caused by Shapley also allows astronomers to study its mass distribution with remarkable precision. This phenomenon occurs when the supercluster's immense gravity bends the light from background galaxies, magnifying and distorting their images. By analyzing these distortions, scientists can map the distribution of dark matter within Shapley and compare it to the visible matter, shedding light on the mysterious relationship between the two. While the observational tools we have today are incredibly powerful, the study of the Shapley Supercluster remains an evolving frontier. Upcoming missions, such as the Euclid Space Telescope and the James Webb Space Telescope, promise to revolutionize our understanding of this colossal structure. These advanced observatories will provide unprecedented data on the supercluster's galaxies, dark matter, and gas, enabling astronomers to test new theories and refine existing ones. One of the most exciting possibilities is the use of Shapley as a natural laboratory for studying the formation and evolution of galaxy clusters. Within the supercluster, galaxies are subjected to intense gravitational forces and frequent interactions, creating an environment that is ideal for triggering star formation, black hole activity, and other astrophysical phenomena. By observing these processes in action, scientists can gain new insights into the life cycles of galaxies and the mechanisms that shape their evolution. The Shapley Supercluster also serves as a window into the distant past. Because light from its galaxies takes hundreds of millions of years to reach us, we see these objects as they were in the distant past, providing a snapshot of an earlier era in cosmic history. By comparing the properties of galaxies within Shapley to those in other regions of the universe, astronomers can trace the evolution of galaxies over time and explore how different environments influence their development. Yet, as much as we have learned from the Shapley Supercluster, it remains a source of profound mystery. For example, recent observations have revealed unexpected asymmetries in its structure, suggesting that it may have undergone a violent merger with another supercluster in the distant past. These findings raise new questions about the dynamics of superclusters and the forces that govern their growth and evolution. In many ways, the Shapley Supercluster is a microcosm of the universe itself, vast, complex, and full of unanswered questions. Its study challenges us to think beyond the boundaries of what we know, inspiring new ideas and pushing the limits of human understanding. As we continue to explore this extraordinary structure, we not only deepen our knowledge of the cosmos but also affirm our place within it as curious and determined seekers of truth. As we venture deeper into the mysteries surrounding the Shapley Supercluster, it becomes clear that it is not just an isolated feature of the universe, but rather an active participant in the ongoing evolution of cosmic structures. Understanding the full extent of its impact requires delving into the nature of galaxy interactions and how they shape both the supercluster itself and the broader cosmic landscape. One of the most intriguing aspects of the Shapley Supercluster is its role in galaxy evolution. The supercluster's enormous gravitational pull draws galaxies toward it, leading to frequent collisions and mergers. These interactions can trigger a variety of fascinating processes. For example, galaxy mergers often result in the formation of new stars, as gas clouds are compressed and ignite. In addition, the central supermassive black holes of merging galaxies can collide, resulting in the release of vast amounts of energy in the form of gravitational waves and high-energy radiation. The gravitational interactions within the Shapley Supercluster also provide a natural environment for studying active galactic nuclei, AGN, regions of galaxies where the central black hole is actively consuming matter. These AGN are among the most powerful sources of radiation in the universe, and understanding how they behave within the dense environment of a supercluster is critical for unraveling the processes that govern black hole growth and the feedback mechanisms that influence galaxy evolution. A particularly captivating example is the Shapley A galaxy, one of the largest galaxies within the supercluster. This galaxy is home to a supermassive black hole that is actively accreting matter, producing an enormous output of energy. The study of such AGNs offers a unique window into the mechanics of black hole growth and the role these cosmic giants play in shaping the evolution of their host galaxies. The Shapley Supercluster is also home to a wide variety of galaxy types, from spiral galaxies similar to our own Milky Way, to elliptical galaxies that have experienced more extensive mergers and interactions. These differences in galaxy types provide important clues about the evolutionary paths that galaxies follow as they move through dense environments like superclusters. For instance, the frequent interactions and mergers within the supercluster are thought to transform spiral galaxies into elliptical galaxies over time, as the gas and stars in the galaxies are redistributed during collisions. This process of transformation is not limited to just a few galaxies. As galaxies fall into the supercluster's gravitational well, their environments change dramatically. The hot gas that fills the space between galaxies in the supercluster, known as the intracluster medium, ICM, plays a key role in this transformation. The ICM is a vast, diffuse plasma that can strip gas from galaxies as they move through it, a process known as ram pressure stripping. This loss of gas can prevent galaxies from forming new stars, effectively halting their evolution into quiescent elliptical galaxies. The immense size and density of the Shapley Supercluster also make it an ideal laboratory for studying the dynamics of galaxy clusters. Clusters are the largest gravitationally bound structures in the universe, and the Shapley Supercluster is home to some of the most massive and densely packed examples. The gravitational forces within these clusters are so strong that they can bend the fabric of spacetime, causing a phenomenon known as gravitational lensing. By studying the way light from distant background galaxies is distorted as it passes through the supercluster, astronomers can map out the distribution of both visible and dark matter within these clusters. Through gravitational lensing, scientists have been able to observe the dark matter halos surrounding galaxy clusters, shedding light on the mysterious nature of dark matter. These halos are thought to contain the majority of the mass in galaxy clusters, and understanding their structure is crucial for deciphering the properties of dark matter itself. In the case of the Shapley Supercluster, these observations have revealed that dark matter is distributed in complex, irregular ways, suggesting that the supercluster may have undergone a series of mergers or interactions in the past. The Shapley Supercluster is also a key piece in the puzzle of understanding the large-scale structure of the universe. While we often think of the universe as an empty, homogeneous expanse, it is actually a vast, interconnected web of galaxies and superclusters, with vast voids between them. These cosmic structures form a complex pattern known as the cosmic web, and the Shapley Supercluster is one of the most prominent nodes in this web. Its position at the intersection of several large-scale cosmic filaments makes it an essential element in the ongoing formation and evolution of the universe's structure. By studying the supercluster's position and motion relative to other structures in the cosmic web, astronomers are gaining insights into the dynamics of cosmic expansion and the influence of dark energy. The Shapley Supercluster, along with other massive structures like the Virgo cluster and the Coma cluster, plays a central role in the formation of these cosmic filaments, which act as the highways along which galaxies travel across the universe. As these galaxies move through the cosmic web, they are influenced by the gravitational forces of nearby superclusters, causing them to accelerate or decelerate depending on the surrounding gravitational landscape. Understanding the movement of the Shapley Supercluster within this cosmic web is also critical for studying the overall evolution of the universe. The motion of superclusters can reveal key information about the expansion rate of the universe, the distribution of dark matter, and the properties of dark energy. The Shapley Supercluster, in particular, is thought to be moving toward the Great Attractor, a mysterious concentration of mass located in the direction of the Hydra and Centaurus constellations. This movement suggests that there are still large-scale gravitational forces at play in the universe, pulling structures like Shapley and the Milky Way toward each other. The study of the Shapley Supercluster is not just an academic pursuit, it has practical implications for our understanding of the universe's past, present, and future. As we continue to unravel its mysteries, we gain new insights into the fundamental forces that govern the cosmos, from the nature of dark matter and dark energy to the processes that drive galaxy evolution and large-scale structure formation. The supercluster's immense scale and complexity challenge our understanding of gravity, motion, and the very fabric of spacetime itself. Looking ahead, the ongoing study of the Shapley Supercluster will likely reveal even more surprising and profound discoveries. As our observational tools become increasingly sophisticated, we will continue to refine our understanding of this colossal structure and its role in shaping the universe. It is clear that the Shapley Supercluster, with its immense gravitational influence and complex dynamics, will remain a central focus of cosmological research for many years to come. The Shapley Supercluster serves as a powerful reminder of the scale and complexity of the universe. Its sheer size and gravitational dominance force us to reconsider our place in the cosmos, challenging our preconceived notions of what is possible and what lies beyond our understanding. As we continue to study this remarkable structure, we are reminded that the universe is far from simple. It is a vast, interconnected web of forces, movements, and mysteries waiting to be unraveled. As we delve deeper into the Shapley Supercluster's influence on the universe, it becomes clear that this cosmic structure isn't just a mere collection of galaxies, but a pivotal player in the grander scheme of things. Its effects ripple across the cosmos, shaping the environment in which galaxies evolve, and offering key insights into the forces at play in our universe. One of the most fundamental effects of the Shapley Supercluster's gravitational pull is on the motion of nearby galaxies, including our own Milky Way. The movement of the supercluster itself, along with the way it affects other structures, can reveal crucial details about the expansion of the universe and the forces that govern cosmic dynamics. The Shapley Supercluster is, in fact, moving towards a mysterious region of space known as the Great Attractor, which lies within the Laniakea Supercluster. The Great Attractor is an area of space that appears to exert a tremendous gravitational influence, pulling objects towards it at surprising speeds. The motion of the Shapley Supercluster towards this region is indicative of the presence of unseen mass in the universe, possibly linked to dark matter or other phenomena yet to be fully understood. As the Shapley Supercluster moves through space, it also exerts a gravitational force on the Milky Way and other neighboring galaxies. The gravitational attraction between these structures affects the motion of the galaxies themselves, creating what could be described as a cosmic dance. The influence of this massive supercluster alters the trajectory of galaxies within it, affecting the speed at which they move and the paths they follow through space. In essence, the Shapley Supercluster is not just a passive collection of galaxies. It is a dynamic, active structure that shapes the environment of nearby galaxies, including our own. The movement of the Shapley Supercluster also has significant implications for the study of cosmology. By analyzing the way this supercluster moves through space, astronomers can refine their understanding of the large-scale structure of the universe. These movements offer valuable clues about the gravitational interactions between superclusters and the distribution of mass across vast cosmic distances. In turn, this can help us better understand how the universe has evolved over billions of years, and how it will continue to evolve in the future. Interestingly, the Shapley Supercluster's motion has also raised questions about dark energy, the mysterious force believed to be accelerating the expansion of the universe. The gravitational pull exerted by the Shapley Supercluster, and the way it moves through space, suggests that the universe's expansion may not be as simple as we once thought. Some theories propose that the supercluster's motion could be influenced by a form of dark energy that is not uniformly distributed across the universe, but rather concentrated in certain regions. This could have significant implications for our understanding of the forces driving the expansion of the universe, and might even provide new insights into the nature of dark energy itself. As we look further into the implications of the Shapley Supercluster's movement and gravitational effects, we must also consider the influence of galaxy clusters within it. The Shapley Supercluster is home to several major galaxy clusters, each of which plays a unique role in shaping the overall structure of the supercluster. These clusters, including the Shapley A cluster, are massive collections of galaxies bound together by gravity, and they serve as important laboratories for studying the interactions between galaxies, dark matter, and the intergalactic medium. The dense environments within these galaxy clusters also provide a fertile ground for studying the evolution of galaxies and their constituent components. The gravitational forces at play within the clusters can trigger the formation of new stars, as gas clouds are compressed and subjected to extreme conditions. In addition, galaxy clusters are home to some of the most powerful phenomena in the universe, such as active galactic nuclei (AGN), where supermassive black holes consume vast amounts of matter, releasing enormous amounts of energy in the process. These AGNs provide an invaluable opportunity to study the behavior of black holes and their impact on the galaxies around them. The central role that galaxy clusters play in the Shapley Supercluster's evolution also highlights the importance of intergalactic space in shaping the universe. The space between galaxies in a cluster is not empty, but is instead filled with a hot, diffuse gas known as the intracluster medium, ICM. This gas plays a crucial role in the evolution of galaxies, as it can strip away gas from galaxies moving through it, preventing them from forming new stars. This phenomenon, known as ram pressure stripping, is one of the ways in which galaxies can evolve from being star-forming spiral galaxies to older, quiescent elliptical galaxies. The study of the Shapley Supercluster's galaxy clusters has provided valuable insights into the complex interactions between galaxies and the ICM. For example, scientists have discovered that galaxies within these clusters often experience galactic harassment, a process in which close encounters between galaxies can lead to the disruption of their structure, triggering the formation of new stars or even the ejection of stars from the galaxy entirely. These interactions can also lead to the formation of galaxy mergers, which play a critical role in shaping the future of galaxies and influencing their evolution over cosmic timescales. As we continue to observe and study the Shapley Supercluster, one of the most profound realizations is the sheer scale of its influence. This massive structure is not just a collection of galaxies. It is a powerful force that shapes the motion of galaxies, triggers the formation of stars, and even plays a role in the creation of black holes. Its gravitational pull reaches far beyond its immediate surroundings, and its impact is felt across vast cosmic distances. But the Shapley Supercluster is not alone in its grandeur. It is just one example of the many superclusters scattered throughout the universe, each contributing to the intricate cosmic web that forms the large-scale structure of the universe. These superclusters are not isolated entities. They are interconnected by vast cosmic filaments, which serve as the highways along which galaxies move. The study of the Shapley Supercluster, and the other superclusters that populate the cosmos, offers an unparalleled opportunity to understand the dynamics of the universe on its largest scales. This exploration of the Shapley Supercluster also serves as a reminder of just how much we have yet to discover about the cosmos. Despite the advances we have made in our understanding of space, the universe remains full of mysteries that continue to challenge our most fundamental assumptions. The Shapley Supercluster, with its vast size, gravitational pull, and complex interactions, is a testament to the infinite complexities that lie beyond our reach. And as we continue to study these cosmic giants, we may find that the answers to our most pressing questions are just waiting to be discovered. The Shapley Supercluster stands as one of the most fascinating and enigmatic objects in the universe. It is not just a massive structure that holds galaxies within its grasp. It is a living, breathing entity that shapes the very fabric of the cosmos. Its study will continue to offer insights into the nature of dark matter, dark energy, galaxy evolution, and the large-scale structure of the universe. The Shapley Supercluster is more than just a collection of stars and galaxies. It is a key to unlocking the deepest mysteries of the universe. As we continue to unravel the mysteries of the Shapley Supercluster, it's crucial to understand that this structure, with its overwhelming gravitational influence, is not an isolated phenomenon. It serves as a window into the much larger and more complex systems that shape the universe. The vast number of galaxies that reside within the Shapley Supercluster are not static. They are constantly in motion, influenced by a web of gravitational forces that extend far beyond the cluster's boundaries. When we examine the supercluster's influence on the motion of galaxies, we must also consider the concept of galactic velocity flows. These flows are the result of the gravitational interactions between the supercluster and other massive cosmic structures, such as neighboring superclusters and dark matter halos. The Shapley Supercluster's immense mass and its motion through space contribute significantly to the peculiar velocities of galaxies, which are velocities that deviate from the expected uniform motion due to the expansion of the universe. The peculiar motion of galaxies in the Shapley Supercluster is not random. It is a direct result of the gravitational pull exerted by the supercluster. This force accelerates, or decelerates galaxies in a way that allows scientists to observe the overall flow of the supercluster. By studying these peculiar velocities, astronomers can estimate the mass of the supercluster and gain valuable insights into its structure. This also gives us a deeper understanding of how gravitational forces act on large scales, further refining our models of cosmic dynamics. A particularly intriguing aspect of the Shapley Supercluster is its contribution to the cosmic flow, the movement of galaxies across vast distances. As it moves toward the Great Attractor, the Shapley Supercluster carries with it galaxies, clusters, and other matter, affecting the motion of surrounding objects. This cosmic flow is a critical factor in the study of large-scale structure formation. It suggests that the universe may not be expanding uniformly. Instead, some regions, like the Shapley Supercluster, are being drawn toward gravitational lenses, created by the mass of other clusters and superclusters. This is reminiscent of a cosmic tug-of-war, where massive structures exert an invisible pull on the surrounding galaxies. When we shift our focus from the motion of galaxies to the composition and structure of the supercluster itself, we encounter a fascinating array of phenomena. The Shapley Supercluster, much like other superclusters, is primarily composed of dark matter, a mysterious substance that makes up a significant portion of the universe's mass. Dark matter does not emit or interact with electromagnetic radiation, making it invisible to traditional telescopes, but its presence can be inferred by observing its gravitational effects on visible matter, such as galaxies and stars. Dark matter plays a critical role in the formation and evolution of large-scale structures like the Shapley Supercluster. It acts as the scaffolding that holds the galaxies and galaxy clusters together. Without dark matter, the gravitational forces in the supercluster would not be sufficient to maintain the cohesive structure of galaxies. This implies that the supercluster is likely surrounded by a massive dark matter halo, which extends far beyond the visible galaxies that make up the cluster. This dark matter halo not only contributes to the supercluster's mass but also influences the motion of galaxies within and outside the cluster. In a sense, the dark matter in the Shapley Supercluster is the silent architect of its existence, unseen but essential for the supercluster's stability. Within the Shapley Supercluster, we find a number of galaxy clusters, which are themselves dense regions of galaxies bound together by gravity. These clusters are the building blocks of the supercluster and provide essential clues about the processes that govern galaxy formation and evolution. Some of the largest and most well-studied clusters within the Shapley Supercluster include the Shapley A cluster and the Shapley B cluster. Each of these clusters is a massive collection of galaxies that are tightly bound by gravitational forces. The galaxies within these clusters are constantly interacting with one another, merging, and exchanging gas, stars, and energy. Interestingly, the galaxies within these clusters don't just interact with each other, they also interact with the intracluster medium, ICM, a hot, diffuse gas that fills the space between galaxies in the cluster. The ICM is made up of ionized gas and is typically heated to millions of degrees Celsius. The presence of the ICM influences the evolution of galaxies in profound ways. For instance, galaxies that pass through the ICM can undergo a process known as ram pressure stripping, where the hot gas in the ICM strips away the outer layers of gas from the galaxy. This process can prevent galaxies from forming new stars, effectively quenching their star formation and transforming them into passive, red elliptical galaxies. Moreover, the interactions between galaxies and the ICM also lead to the formation of some of the most spectacular cosmic phenomena, such as shock waves and radio jets. These jets are often associated with active galactic nuclei (AGN), supermassive black holes at the centers of galaxies. As these black holes accrete matter, they release vast amounts of energy in the form of jets that can extend across millions of light years. The presence of these jets provides valuable information about the processes occurring in the supercluster and offers a glimpse into the extreme environments around supermassive black holes. As we zoom out to consider the Shapley Supercluster in the broader context of the universe, it's important to note that superclusters like Shapley are not isolated. They are part of a vast cosmic web. This web is a network of filaments, clusters, and superclusters that connect the largest structures in the universe. The Shapley Supercluster is one of many such structures, and its location within this web is key to understanding how matter is distributed throughout the cosmos. The web-like structure of the universe suggests that galaxies are not scattered randomly across space, but are instead organized into large-scale structures that are connected by vast, invisible filaments of dark matter. The study of superclusters and their place in the cosmic web has far-reaching implications for our understanding of the large-scale structure of the universe. By analyzing how superclusters like Shapley interact with their surroundings, scientists can gain insights into the forces that govern the evolution of the universe. These interactions help to reveal the distribution of dark matter and dark energy, two of the most mysterious components of the cosmos. Furthermore, as we continue to investigate the Shapley Supercluster, we are also uncovering more about the history of the universe itself. Superclusters, by their very nature, are ancient structures. They have been evolving for billions of years, and their study allows us to peer into the past and understand the processes that have shaped the universe over time. By examining the distribution of galaxies within the Shapley Supercluster and other superclusters, astronomers can trace the growth of cosmic structures and gain a deeper understanding of the forces that have driven the expansion of the universe since the Big Bang. Looking to the future, the Shapley Supercluster will continue to be a critical object of study for astronomers. With the advent of new technologies, such as the James Webb Space Telescope and the next-generation Very Large Array, (NVLA), scientists will be able to observe the Shapley Supercluster in unprecedented detail. These new instruments will provide a clearer picture of the supercluster's composition, structure, and dynamics, offering deeper insights into its role in the cosmos. The Shapley Supercluster is far more than just a collection of galaxies. It is a dynamic and influential structure that plays a central role in the evolution of the universe. From its gravitational influence on neighboring galaxies to its interaction with the intracluster medium, the supercluster offers a wealth of information about the forces that shape the cosmos. As we continue to study this extraordinary cosmic structure, we will uncover even more about the nature of dark matter, dark energy, and the large-scale structure of the universe. The Shapley Supercluster is a testament to the complexity and beauty of the universe, a structure that continues to challenge our understanding and inspire our curiosity. As we dive deeper into the cosmic web that the Shapley Supercluster is a part of, it becomes evident that its significance extends beyond just its gravitational influence. The supercluster provides a lens through which we can study the vast interconnectedness of all matter in the universe. The large-scale structure of the universe is composed of galaxy clusters, superclusters, and filaments that form a vast network, with galaxies arranged in long, dense chains separated by voids. The Shapley Supercluster plays a critical role in this cosmic structure, helping to shape the way galaxies move and evolve. One of the fascinating aspects of studying the Shapley Supercluster is the way it helps us understand galaxy evolution. When galaxies are part of a massive structure like the Shapley Supercluster, their evolution is significantly impacted by the environment around them. The high density of galaxies in a supercluster means that galaxies are more likely to collide or merge with one another. These galactic interactions can lead to the formation of new types of galaxies, including elliptical galaxies, which are often formed when two spiral galaxies merge. These interactions also trigger bursts of star formation, as gas clouds within the galaxies compress and collapse, leading to the birth of new stars. Another key feature of the Shapley Supercluster is its dense core. The center of the supercluster is packed with several massive galaxy clusters, including the Shapley A cluster. This dense central region is home to some of the most extreme environments in the universe. The galaxy clusters here are so massive that their gravitational pull can distort space-time itself. This warping of space-time, predicted by Einstein's theory of general relativity, creates what we call gravitational lensing. Gravitational lensing occurs when the gravity of a massive object, like a galaxy cluster, bends the light coming from a more distant object. This phenomenon allows astronomers to study faraway galaxies and objects that would otherwise be too faint to observe. The Shapley Supercluster's core is thus not only an area of extreme gravitational influence, but also a unique natural laboratory for studying the fabric of space-time. The Shapley Supercluster's immense gravitational power does not only affect galaxies within it, it also influences the motion of galaxies outside of its boundaries. The Shapley Supercluster's sheer mass is causing nearby galaxies to be pulled toward it, a process that is not only changing the trajectories of these galaxies but also contributing to a phenomenon known as the Great Attractor. The Great Attractor is a mysterious, massive region of space that is drawing galaxies in from all directions. It is still not fully understood, but the gravitational forces of the Shapley Supercluster are believed to be a key part of this cosmic pull. As we shift our focus to the larger, more cosmological scale, the Shapley Supercluster represents a snapshot of the universe's complex history. Its formation can be traced back billions of years, and its current structure is the result of countless cosmic events. The process of cosmic growth, the expansion of the universe, has shaped the Shapley Supercluster in profound ways. As the universe expands, matter has clumped together under the force of gravity to form galaxies, clusters, and superclusters. The Shapley Supercluster is a direct result of this ongoing process. It is a relic of the early universe, and studying it provides us with clues about how large structures in the universe have evolved over time. However, as awe-inspiring as it is, the Shapley Supercluster is also a reminder of the transitory nature of cosmic structures. The universe is constantly in motion, and over billions of years, the Shapley Supercluster will continue to evolve. Eventually, the galaxies within the supercluster may merge into even larger clusters or disperse under the influence of other cosmic forces. The dark matter halo that surrounds the supercluster may also shift and change over time, affecting the motion of galaxies within the cluster. The future of the Shapley Supercluster and its place in the universe raises intriguing questions about the ultimate fate of superclusters and galaxy clusters. Will they continue to grow and evolve, forming even larger structures, or will they eventually dissipate, leaving behind a more uniform distribution of matter? These questions remain at the forefront of cosmological research, as scientists continue to study the evolution of the universe on the largest scales. In the coming decades, astronomers will gain even more powerful tools for studying the Shapley Supercluster and other superclusters. The advent of next-generation telescopes and space observatories, such as the James Webb Space Telescope and the Square Kilometre Array, will provide us with unprecedented views of the universe. These technologies will allow us to observe the high-energy phenomena occurring within the Shapley Supercluster, such as the interaction of galaxy clusters, the behavior of black holes, and the distribution of dark matter. With these new instruments, we may finally be able to answer some of the lingering questions about the supercluster's role in the universe and its connection to the larger cosmic web. The Shapley Supercluster's importance extends beyond just its role in the motion of galaxies. It also serves as a key piece in the puzzle of understanding the mystery of dark matter. Dark matter is thought to make up around 85% of the universe's mass, but it has never been directly observed. Its presence is inferred by the gravitational effects it has on visible matter. The Shapley Supercluster, with its vast collection of galaxies and the associated dark matter halo, is one of the best places to study the distribution and behavior of dark matter. By observing the motion of galaxies and the bending of light in the supercluster, astronomers hope to uncover more about the elusive nature of dark matter. Furthermore, the Shapley Supercluster provides a glimpse into the distribution of mass in the universe. The supercluster's mass influences the gravitational flow of galaxies, and studying this flow can give us a better understanding of how mass is spread out across the universe. This is a critical piece of the puzzle in understanding the evolution of large-scale cosmic structures and the future of the universe. The Shapley Supercluster stands as a testament to the complexity of the universe's large-scale structure. It is a massive, gravitationally influential system of galaxies, dark matter, and cosmic forces that has shaped the motion of galaxies for billions of years. Its study offers valuable insights into the forces that govern the universe and the role of dark matter in the formation of cosmic structures. As we continue to explore the Shapley Supercluster and other superclusters, we move one step closer to unraveling the deepest mysteries of the cosmos. From understanding the nature of dark matter to exploring the dynamics of galactic motion, the Shapley Supercluster will remain a crucial area of study for astronomers and cosmologists alike, helping us understand not only the universe's past but also its future. As we push further into the depths of space and explore the mechanics of the Shapley Supercluster, we encounter an ever-expanding universe of mysterious phenomena and cosmic puzzles. The Shapley Supercluster, with its staggering mass and immense gravitational influence, offers a unique vantage point for understanding the large-scale structure of the universe. Its existence challenges our comprehension of galactic behavior, interactions, and the very nature of space-time itself. With its influence extending across vast distances, It acts as both a cosmic bridge and a cosmic anchor, linking galaxies across the universe while simultaneously serving as a center of immense gravitational force. One of the most intriguing aspects of the Shapley Supercluster is its role in the evolution of galaxy clusters. As mentioned before, the supercluster's central regions, which are home to some of the universe's most massive galaxy clusters, provide a laboratory for studying the dynamics of galactic mergers and interactions. These interactions are essential to understanding the formation and evolution of galaxies, as well as their eventual fates. When galaxies collide or pass close to one another, their interstellar gas clouds can compress and trigger waves of star formation, often resulting in new, young stars. But these galactic collisions can also end in tragedy, as galaxies may strip away the gas and dust needed to form new stars, eventually leading to their quiescent end as elliptical galaxies. The Shapley Supercluster's immense gravity ensures that these interactions happen frequently, creating a complex and evolving tapestry of galaxies. At the same time, the Shapley Supercluster is also home to some of the oldest, most evolved galaxies in the universe. These galaxies are relics from the early universe, having formed billions of years ago and evolved under the influence of their gravitationally dominant environment. Understanding the Shapley Supercluster allows us to study the evolution of galaxies over cosmic timescales, from the formation of early spiral galaxies to the final stages where galaxies settle into more passive, elliptical forms. These galaxies are valuable time capsules, providing a glimpse into the past and offering insight into how galaxies will continue to evolve in the future. The influence of the Shapley Supercluster is also seen in the phenomenon known as cosmic flow. This refers to the way galaxies move within the universe due to the gravitational pull of massive objects. The Shapley Supercluster is a key player in this cosmic flow, particularly in the context of its role in drawing galaxies toward it. This motion has profound consequences on the structure of the universe. The flow of galaxies towards superclusters like Shapley hints at the cosmic web, a large-scale network of filaments, voids, and clusters that make up the universe's structure. This web-like network is not only a collection of objects but also the underlying framework that shapes the motion of galaxies and the distribution of matter throughout the universe. By studying the Shapley Supercluster, we can better understand how the cosmic web functions and how galaxies interact within it. It is essential to highlight that while the Shapley Supercluster's gravitational influence is significant, its role in the broader cosmological picture is still an ongoing area of research. The supercluster is part of a larger structure of interconnected superclusters that form the cosmic network of the universe. These superclusters are thought to be the largest gravitationally bound structures in the universe, yet they are part of a dynamic system, interacting and evolving over vast time periods. The Shapley Supercluster itself is influenced by surrounding superclusters and, in turn, influences others through gravitational attraction. This interconnectedness is a fundamental feature of the universe's evolution and a topic that astronomers are actively exploring. As we look at the future of the Shapley Supercluster and its place in the cosmic order, there are several key questions that still remain unanswered. One of the most significant is the ultimate fate of the supercluster. The universe is expanding at an accelerating rate, and this expansion will have profound effects on the future dynamics of the Shapley Supercluster. As space continues to stretch, the gravitational bonds that hold superclusters together may weaken. Galaxies may eventually become isolated from each other, and structures like the Shapley Supercluster could break apart, leaving behind a more sparsely populated universe. The outcome of this process is still uncertain, and understanding it requires further study of the expansion of the universe and its influence on the largest cosmic structures. Moreover, as technology advances, we are gaining access to new observational tools that could revolutionize our understanding of the Shapley Supercluster. The next generation of space telescopes, including the James Webb Space Telescope, are poised to provide unparalleled views of the supercluster's core and its distant reaches. These instruments will allow astronomers to observe the dark matter and gravitational lensing effects in even more detail, revealing insights into the underlying structure of the supercluster and the mysterious forces that govern its behavior. With the ability to detect faint signals from the most distant galaxies and clusters, these telescopes will provide invaluable data that could lead to the discovery of new phenomena within the Shapley Supercluster. In addition, the study of gravitational waves, ripples in spacetime caused by massive objects like merging black holes and neutron stars, could offer another exciting avenue of exploration. The Shapley Supercluster, with its dense concentration of galaxies and the presence of supermassive black holes at the centers of many of these galaxies, may be a source of gravitational waves that can be detected by advanced observatories like LIGO, Laser Interferometer Gravitational Wave Observatory. These waves carry information about the most extreme events in the universe, offering insights into the behavior of black holes, galaxy mergers, and the nature of spacetime itself. Studying gravitational waves from the Shapley Supercluster could uncover new aspects of its complex dynamics and provide a deeper understanding of how massive objects interact within this colossal structure. The Shapley Supercluster also holds promise for studying one of the most perplexing mysteries in modern cosmology: the nature of dark energy. Dark energy is the hypothetical force responsible for the accelerated expansion of the universe. While its exact nature remains elusive, the study of large-scale structures like the Shapley Supercluster can help scientists constrain theories of dark energy. By observing the motion of galaxies within the supercluster and measuring how the supercluster's mass is distributed, astronomers may be able to infer the properties of dark energy and its role in shaping the evolution of the universe. This, in turn, could lead to new discoveries about the fundamental forces that govern all matter and energy in the cosmos. One final aspect worth considering is the potential for future intergalactic exploration. While current technology limits us to observing distant galaxies from afar, the study of superclusters like the Shapley Supercluster opens the door to the possibility of future space exploration on a much larger scale. In the distant future, as technology advances, humanity may find ways to travel across vast distances of space, potentially exploring the edges of superclusters and the dark voids between them. This concept may seem far-fetched, but as our understanding of space and time grows, so too does the possibility of venturing into the heart of such cosmic giants. The Shapley Supercluster is not just a collection of galaxies, it's a complex, dynamic system that influences the motion of galaxies, drives cosmic interactions, and helps shape the evolution of the universe. Its massive size and gravitational force make it one of the most significant structures in the cosmos, and its study holds the key to unlocking some of the universe's greatest mysteries. From understanding galaxy formation and dark matter to exploring the future of the universe itself, the Shapley Supercluster offers a window into the deepest workings of the cosmos. As we continue to explore its mysteries, we move one step closer to understanding the vast and interconnected universe we call home. As we continue to unravel the secrets of the Shapley Supercluster, we begin to see that it is not just a point of interest within our cosmic neighborhood, but rather a key piece in the broader puzzle of the universe's structure. The supercluster's influence extends far beyond our immediate surroundings, reaching out and shaping the very fabric of space-time. Understanding the intricate dynamics of this cosmic giant has profound implications for our comprehension of the universe at large, from its beginning to its ultimate fate. One of the more striking features of the Shapley Supercluster is its proximity to the Great Attractor, a mysterious gravitational anomaly that lies just beyond it, in the direction of the Centaurus and Hydra constellations. The Great Attractor exerts an immense gravitational pull on the Shapley Supercluster, along with many other nearby superclusters, including our own Virgo supercluster. This force is so powerful that it influences the motion of entire galaxy clusters, compelling them to move towards it at speeds of up to 2,200 kilometers per second. The true nature of the Great Attractor remains one of the greatest unsolved mysteries in cosmology. It is believed to be a massive concentration of matter, possibly a supermassive black hole or a dense region of dark matter, but its exact composition is unknown due to the fact that it is obscured by the dense plane of the Milky Way. Despite this, its gravitational effects on the Shapley Supercluster and the universe at large are undeniable. The discovery of the Great Attractor and its connection to the Shapley Supercluster has opened up a new avenue of research in cosmology, as scientists begin to understand how superclusters, and even entire galaxy filaments, are influenced by unseen forces lurking in the far reaches of space. In fact, the study of these gravitational anomalies challenges our understanding of the distribution of mass and energy in the universe. If the Great Attractor truly is a massive, unseen structure, it would imply that the universe is not a uniform expanse, as previously believed, but rather a vast, interconnected web of structures with immense gravitational effects that we are only beginning to comprehend. The Shapley Supercluster is not merely an isolated entity. It is a vital component of a larger cosmic network that is continuously evolving, driven by the gravitational forces at play. Looking deeper into the structure of the Shapley Supercluster itself, one can begin to appreciate the immense scale and complexity of the system. As we discussed earlier, the supercluster is made up of numerous galaxy clusters, each containing millions of individual galaxies. These clusters are not randomly distributed but are instead interconnected by vast filaments of dark matter, which form the backbone of the cosmic web. The gravitational pull of the Shapley supercluster, along with the influence of other nearby superclusters, creates a cosmic tapestry of galaxies that is constantly shifting and evolving. It is a dynamic system, with galaxies constantly moving towards and away from one another, colliding, merging, and forming new structures in the process. The existence of the Shapley supercluster also raises important questions about the large-scale distribution of dark matter. Dark matter, which is invisible and detectable only through its gravitational effects, makes up about 27% of the universe's total mass energy content. Yet, its true nature remains one of the greatest enigmas in modern physics. The Shapley supercluster, with its massive concentrations of galaxies and dark matter, serves as an ideal laboratory for studying this mysterious substance. By observing how galaxies within the supercluster move and interact, scientists can gain valuable insights into the distribution of dark matter and how it influences the behavior of large-scale cosmic structures. These observations could eventually lead to a breakthrough in our understanding of dark matter, helping to answer one of the most fundamental questions in astrophysics. One particularly intriguing aspect of the Shapley supercluster is the possibility of dark energy being a key player in its evolution. Dark energy, the mysterious force responsible for the accelerated expansion of the universe, is thought to make up about 68% of the total energy content of the cosmos. It has been observed that the universe's expansion is speeding up, a phenomenon that has profound implications for the ultimate fate of the universe. While dark energy is believed to be driving the expansion, its exact nature is still poorly understood. The Shapley supercluster's proximity to the Great Attractor and the cosmic flow of galaxies towards it raises the possibility that dark energy plays a role in shaping the movement of entire superclusters. If dark energy is responsible for the accelerated expansion, it might also be influencing how structures like the Shapley supercluster are organized and how they evolve over time. As scientists continue to observe and analyze the Shapley supercluster, there is hope that new technologies will unlock more secrets about its composition and behavior. The next generation of space telescopes and gravitational wave observatories are poised to provide more precise measurements of the supercluster's mass, structure, and gravitational effects. Instruments like the James Webb Space Telescope and the Square Kilometre Array will offer new insights into the distant regions of the Shapley supercluster, allowing astronomers to study its galaxies, clusters, and dark matter in unprecedented detail. These observations will provide crucial data that could lead to breakthroughs in our understanding of cosmic structure, dark matter, and dark energy. One of the key challenges in studying superclusters like Shapley is the immense distance that separates us from them. The Shapley supercluster lies about 650 million light-years away, making it difficult to study in detail. However, the advancement of technology is enabling astronomers to overcome this challenge. For example, the Event Horizon Telescope, which famously captured the first image of a black hole in the Messier 87 galaxy, could potentially be used to study the supermassive black holes at the centers of galaxies within the Shapley supercluster. These supermassive black holes play a crucial role in the formation and evolution of galaxies, and understanding them is key to understanding the dynamics of the supercluster as a whole. As our understanding of the Shapley supercluster deepens, we are also confronted with questions about the ultimate fate of this colossal structure. Will it continue to grow as galaxies merge and cluster together under the influence of gravity? Or will the expansion of the universe eventually cause it to break apart? While the future of the universe is still uncertain, the study of superclusters like Shapley provides valuable clues about the long-term evolution of the cosmos. By understanding the forces at play within these massive structures, we can begin to predict how the universe will evolve in the distant future. The Shapley Supercluster is more than just a collection of galaxies. It is a cosmic colossus that serves as a testbed for understanding the large-scale structure of the universe. Its immense gravitational influence on surrounding galaxies and superclusters offers a window into the workings of the cosmos, from the formation of galaxies to the dynamics of dark matter and dark energy. The study of this supercluster, along with others like it, is key to unraveling the deepest mysteries of the universe. As technology continues to advance, so too will our ability to explore and understand the Shapley Supercluster and the countless other cosmic structures that shape the universe. The journey of discovery has only just begun. As we continue to probe the Shapley Supercluster and its many mysteries, it becomes clear that its gravitational influence on the surrounding universe is not just limited to its immediate vicinity. In fact, its vast scale and the immense forces at play have far-reaching consequences for the movement of entire galaxy clusters and the overall structure of the cosmos. Understanding how these colossal systems interact is not only important for mapping the universe's evolution, but also for gaining insights into the very laws of physics that govern its behavior. In addition to the Great Attractor, another fascinating feature of the Shapley Supercluster is its relationship with the Laniakea Supercluster, a massive collection of galaxy clusters that includes our own Virgo Supercluster, the region of space that contains the Milky Way. The Laniakea Supercluster, which spans over 520 million light-years, is home to 100,000 galaxies, and is gravitationally connected to the Shapley Supercluster through the complex web of galaxy clusters and dark matter filaments that permeate the universe. Though the two superclusters are separated by hundreds of millions of light-years, the gravitational influence of the Shapley Supercluster reaches out to affect galaxies far beyond its immediate neighborhood, making it a key player in the larger cosmic structure. Recent research has shed light on how these superclusters and their interconnected filaments of dark matter play a crucial role in the formation of the large-scale cosmic web. Rather than being spread out evenly throughout the universe, galaxies tend to congregate along vast filaments of dark matter, forming clusters and superclusters that are interconnected by these invisible structures. These filaments, which span vast distances, act as highways for galaxies, guiding their movements through space. The Shapley Supercluster is one of the largest such structures in the universe, and its influence is felt across millions of light-years, affecting the motion of galaxies and even helping to shape the overall expansion of the universe. In fact, the cosmic web theory, which describes the large-scale structure of the universe, suggests that the majority of the mass in the universe is concentrated in these vast filaments of dark matter. These filaments connect the largest galaxy clusters, like the Shapley Supercluster, and stretch across the entire observable universe. As galaxies move through this network of filaments, they experience the gravitational pull of the matter contained within them. This gravitational interaction shapes the motion of galaxies and influences the formation of large-scale structures, such as superclusters and voids. But what is the significance of this for the future of the universe? The motion of galaxies within the cosmic web, particularly the influence of superclusters like Shapley, suggests that the universe is far from being in a state of perfect equilibrium. Instead, it is a dynamic, constantly evolving system, where galaxies are in motion and gravitational forces are continuously at work. While the expansion of the universe is accelerating, the gravitational pull of massive structures like the Shapley Supercluster is still strong enough to overcome this expansion in certain regions. This interaction between the forces of gravity and dark energy will play a crucial role in the future evolution of the universe, and the Shapley Supercluster is a vital part of this process. As we begin to understand the role that the Shapley Supercluster plays in shaping the universe's large-scale structure, we are also confronted with the realization that much of what we know about the cosmos may still be incomplete. While our current theories about dark matter, dark energy, and the distribution of galaxies are based on substantial evidence, there is still much that we don't fully understand. For example, although dark matter is believed to make up the majority of the mass in the universe, we have yet to directly detect it. Instead, we infer its presence through its gravitational effects on visible matter, like galaxies and galaxy clusters. This makes the study of structures like the Shapley Supercluster even more critical. By studying how dark matter behaves within such a massive system, scientists can gain valuable insights into its properties and behavior. New technologies, such as the Large Hadron Collider, LHC, are helping to explore the fundamental nature of dark matter, and the next generation of space telescopes and observatories, such as the James Webb Space Telescope and the Square Kilometre Array, are poised to provide even more data about the cosmos. These advancements will allow scientists to better understand the nature of dark matter, dark energy, and the forces that shape the universe. But even as we delve deeper into the cosmic web and its many mysteries, we are constantly reminded of just how vast and unknowable the universe is. The Shapley Supercluster is one of the largest structures in the universe that we can observe, but it is only a small part of a much larger, and still largely unexplored cosmos. There are likely other superclusters, filaments, and regions of space that we have yet to discover, and these hidden structures could provide even more clues about the nature of the universe and its origins. As we continue to study the Shapley Supercluster and its surrounding environment, we are also confronted with the reality that our understanding of the universe is still in its infancy. While we have made incredible strides in understanding the large-scale structure of the cosmos, there is still much to learn about the forces at play. The Shapley Supercluster represents a fascinating piece of this puzzle, and by studying it, we can gain a deeper understanding of the nature of the universe, the forces that shape it, and its ultimate fate. Ultimately, the study of the Shapley Supercluster is about more than just understanding the motion of galaxies and the behavior of dark matter. It is about gaining a deeper appreciation for the vastness and complexity of the universe, and recognizing that we are only just beginning to scratch the surface of its many mysteries. The Shapley Supercluster, like so many other cosmic structures, holds secrets that we have yet to uncover, and as our tools and technologies continue to improve, we are poised to make even more groundbreaking discoveries in the years to come. As we peer deeper into the heart of this colossal structure, we are reminded of just how interconnected everything in the universe truly is. The Shapley Supercluster is not just an isolated collection of galaxies, but a vital part of the larger cosmic network. It is a testament to the power of gravity, the influence of dark matter, and the interconnectedness of all things in the universe. The more we learn about this vast system, the more we realize that the universe is not a collection of random objects scattered throughout space, but a vast, dynamic, and interconnected whole, where every galaxy, every cluster, and every supercluster plays a role in the larger cosmic dance. The story of the Shapley Supercluster is still unfolding, and as we continue to explore its many mysteries, we will undoubtedly uncover new truths about the universe, the forces that govern it, and our place within it. In the end, the study of this incredible supercluster is not just about understanding the nature of space, but about pushing the boundaries of human knowledge and exploration, reminding us that there is still so much to learn and discover in the vast, mysterious universe that surrounds us. As we continue our exploration of the Shapley Supercluster and its profound impact on the cosmos, it's essential to dive deeper into the ways this immense structure influences the dynamics of the universe around it. Understanding the Shapley Supercluster's gravitational pull helps us paint a more accurate picture of the intricate forces that shape the universe. The more we learn about these interactions, the more we realize just how interconnected everything in the cosmos truly is. One of the most remarkable features of the Shapley Supercluster is its gravitational influence on the motion of our Milky Way galaxy. As we previously mentioned, the Shapley Supercluster is not just a random collection of galaxies. It is a massive, interconnected structure whose gravitational pull affects the movement of nearby galaxies. Our galaxy, the Milky Way, is currently moving towards this supercluster at an astonishing speed of around 1.3 million miles per hour, 2.1 million kilometers per hour. This motion, known as the peculiar motion of the Milky Way, is influenced by the gravitational forces exerted by the Shapley Supercluster. The Great Attractor, located within the Shapley Supercluster, plays a key role in this. It is a mysterious region of space where the gravitational forces are so intense that they affect the motion of galaxies over vast distances. The Milky Way, along with many other galaxies in our cosmic neighborhood, is being drawn towards this region. This movement suggests that the universe is far from static and that gravitational interactions continue to shape the evolution of galaxies and galaxy clusters. The Shapley Supercluster, with its immense mass, is the primary driver of this cosmic motion. This leads to a fascinating question: how much does the Shapley Supercluster's gravity influence the Milky Way's future? The current trajectory of the Milky Way is not set in stone. As we move towards the Great Attractor, we may eventually encounter a collision with other galaxies in the cluster. While such collisions take billions of years to unfold, they are still significant events that could reshape the structure of our galaxy and the universe as a whole. Interestingly, the Shapley Supercluster's pull is not just affecting our galaxy's motion. It is also part of a larger network of superclusters that are all interconnected through filaments of dark matter. These invisible structures form the cosmic web, and the movement of galaxies along this web is influenced by the gravitational forces exerted by superclusters like Shapley. In essence, the Shapley Supercluster is part of a larger cosmic dance where galaxies are constantly being pulled and pushed by the forces at play in the universe. The cosmic web is one of the most striking features of the large-scale structure of the universe. The dark matter filaments that connect galaxies and superclusters are invisible, yet they form an essential framework that shapes the universe's evolution. These filaments act as highways for galaxies, guiding them along paths determined by the distribution of matter. The Shapley Supercluster, as one of the largest and most massive superclusters in the observable universe, exerts a significant force on the surrounding filaments. This force influences the motion of galaxies, and as a result, the structure of the universe continues to evolve over billions of years. While the Shapley Supercluster's role in shaping the large-scale structure of the universe is undeniable, there are still many unknowns. For instance, despite its massive gravitational influence, the Shapley Supercluster is just one part of the larger cosmic web. There are other superclusters and structures that we have yet to fully understand. One of the biggest challenges for astronomers is determining how many other superclusters like Shapley exist, and how their interactions might affect the broader universe. One possible explanation for the movement of galaxies towards structures like the Shapley Supercluster is the phenomenon known as dark flow. Dark flow is a term used to describe the motion of galaxies that seems to defy the predictions made by the standard model of cosmology. It suggests that large-scale gravitational influences, like those exerted by the Shapley Supercluster, may be causing galaxies to move in a direction that does not align with the expansion of the universe. While dark flow remains a topic of debate among scientists, it highlights the complexity of the universe and the many factors that contribute to the motion of galaxies. The future of the Shapley Supercluster and its impact on the universe remains a subject of intense research. As scientists continue to study the supercluster's motion and its gravitational effects on nearby galaxies, we are gaining a clearer picture of how the universe is evolving. However, there is still much to learn. The next generation of telescopes and observational tools, such as the James Webb Space Telescope, will provide valuable data that will help us understand the Shapley Supercluster's role in shaping the universe's future. Another area of interest is the relationship between the Shapley Supercluster and the dark energy that is causing the accelerated expansion of the universe. While dark matter exerts a gravitational pull, dark energy seems to have the opposite effect. It causes galaxies to move away from each other at an accelerating rate. Understanding how these two forces interact within the Shapley Supercluster could provide insights into the larger mystery of dark energy and its role in the universe's fate. This brings us to one of the most profound questions in cosmology. What is the ultimate fate of the universe? Will the gravitational forces of superclusters like Shapley eventually cause galaxies to collapse back together in a big crunch? Or will the expansion driven by dark energy continue to accelerate, pushing galaxies farther apart? While the Shapley Supercluster is an important piece of this cosmic puzzle, It is only through continued observation and study that we will begin to answer these questions. As we explore the universe and uncover more about the Shapley Supercluster and its vast influence, we are reminded of how much we still don't know. The universe is a vast, dynamic system, constantly evolving and changing in ways we are only beginning to understand. The Shapley Supercluster represents a key piece of this puzzle, but it is just one of many mysteries that continue to challenge our understanding of the cosmos. The story of the Shapley Supercluster is far from over. As new technologies and research methods emerge, we will undoubtedly uncover more about its structure, its role in the cosmic web, and its influence on the evolution of the universe. The more we learn, the more we realize how little we truly know. And in this realization lies the beauty of exploration. There will always be more to discover, more to learn, and more mysteries to unravel in the infinite expanse of the universe. As we continue to peel back the layers of the Shapley Supercluster's enigmatic influence, we begin to encounter even more fascinating aspects of its role within the broader universe. As we dive deeper into this cosmic structure, it becomes increasingly clear that the Shapley Supercluster is not merely a point of interest within our local universe, but rather a key player in the intricate dance of galaxies and gravitational forces that shapes the fabric of the cosmos. One of the critical features that researchers are still trying to fully comprehend is the distribution of galaxies within the Shapley Supercluster. When astronomers observe the structure of the supercluster, they notice that the galaxies are not distributed randomly but instead form distinct patterns, indicating some form of order. These galaxies seem to be pulled toward the dense core of the supercluster, a region where the gravitational pull is strongest. The core itself is home to massive galaxy clusters, which are essentially collections of galaxies that have coalesced over time due to their mutual gravitational attraction. At the heart of the Shapley Supercluster lies a concentration of these galaxy clusters, creating an environment of intense gravitational interactions. The individual galaxies within these clusters interact in various ways, sometimes merging, other times colliding, or simply moving through one another in a complex web of forces. The result is a dynamic, ever-changing system of galaxies that is constantly evolving. These interactions, along with the immense gravitational pull of the supercluster, have profound effects on the orbits and motions of the galaxies involved. Over billions of years, these forces lead to the evolution of the galaxies themselves, causing them to undergo significant transformations. For example, galaxies that were once isolated and independent may eventually merge to form larger, more massive systems, resulting in a reshaping of the local universe. Understanding how galaxies within the Shapley Supercluster move and evolve can also provide us with valuable insights into the long-term behavior of galaxy clusters. When galaxies collide and merge, the resulting gravitational forces can trigger the formation of new stars, the disruption of existing star systems, and the formation of active galactic nuclei (AGN) that emit vast amounts of energy. These active nuclei are often the result of supermassive black holes at the centers of galaxies consuming matter at an astonishing rate. The process of galaxy mergers within the Shapley Supercluster could, in theory, lead to the formation of even more energetic and dynamic AGN, potentially giving rise to new cosmic phenomena that we have yet to fully understand. Beyond the interactions within the Shapley Supercluster itself, it's important to recognize its place within the larger cosmic structure. The universe is not only made up of superclusters and galaxies but also contains vast regions of voids, areas where matter is sparse, and gravitational forces are weaker. The superclusters, including the Shapley Supercluster, act as the skeleton of the universe, with the voids serving as the gaps between these massive structures. The distribution of superclusters and voids throughout the universe creates a delicate balance between regions of high and low gravitational forces, and this balance plays a critical role in shaping the overall structure of the cosmos. The Shapley Supercluster, as one of the largest known gravitational forces in the observable universe, also provides a valuable testing ground for our understanding of cosmological models. For decades, scientists have used simulations and observations to try to understand how the universe formed and how structures like superclusters evolved. The Shapley Supercluster's immense size and gravitational influence make it a prime subject for studying how matter has been distributed throughout the universe over billions of years. By analyzing the distribution of galaxies within the supercluster and their motion, astronomers can refine their models of the Big Bang and the subsequent evolution of the universe. Another fascinating aspect of the Shapley Supercluster is its potential connection to the cosmic microwave background (CMB) radiation, the faint afterglow of the Big Bang that permeates the entire universe. The CMB provides crucial information about the early stages of the universe, and by studying how the Shapley Supercluster affects this radiation, scientists can gain insights into the role of massive structures in shaping the universe's evolution. The presence of large-scale structures like the Shapley Supercluster may even have contributed to the slight temperature fluctuations seen in the CMB, which could provide valuable clues about the distribution of matter and energy in the early universe. As we explore these connections, it becomes clear that the Shapley Supercluster's influence extends far beyond its immediate vicinity. The supercluster is part of a much larger cosmic web, a vast network of galaxies, superclusters, and dark matter that forms the backbone of the universe. The gravitational pull of the Shapley Supercluster, along with other superclusters and dark matter filaments, helps shape the large-scale structure of the cosmos, influencing the motion of galaxies and guiding their paths through the universe. One of the most significant questions that remains unanswered is the role of dark matter in the Shapley Supercluster. Dark matter, which makes up a substantial portion of the universe's mass, is invisible and cannot be directly observed. However, its presence is inferred through its gravitational effects on visible matter. In the case of the Shapley Supercluster, dark matter plays a crucial role in holding the structure together. The galaxies within the supercluster are moving faster than can be explained by the gravitational pull of ordinary matter alone, suggesting that dark matter is exerting a significant influence on the cluster's dynamics. Dark matter is believed to be responsible for the extra mass that is needed to account for the gravitational forces observed within the Shapley Supercluster. While the exact nature of dark matter remains one of the greatest mysteries in modern physics, its presence is undeniable. As scientists continue to study the Shapley Supercluster and other large-scale structures, they hope to uncover more about the properties of dark matter and its role in the formation and evolution of galaxies and superclusters. The Shapley Supercluster is also closely tied to the ongoing mystery of dark energy, the force that is driving the accelerated expansion of the universe. Dark energy is believed to make up about 70% of the total energy content of the universe, and its effects are most pronounced on the largest scales. While the Shapley Supercluster's gravity is pulling galaxies towards it, dark energy is working in the opposite direction, causing the universe to expand at an ever-accelerating rate. Understanding the interplay between these two forces, dark matter and dark energy, is crucial for gaining a complete understanding of the universe's fate. As we stand on the brink of further discovery, the Shapley Supercluster remains a key player in our quest to understand the universe. It is a vast and complex structure that is still shrouded in mystery, but every new observation brings us closer to unraveling its secrets. The gravitational forces exerted by the Shapley Supercluster influence not only the galaxies within it but also the motion of galaxies far beyond its reach. Its effects on the large-scale structure of the universe are profound, and its study may hold the key to answering some of the most fundamental questions in cosmology. With the advancements in technology, the future of cosmological research looks bright. The James Webb Space Telescope, the Large Hadron Collider, and other state-of-the-art instruments are providing new data that could shed light on the nature of dark matter, dark energy, and the structure of the universe. As we continue to study the Shapley Supercluster and its role in the cosmos, we will undoubtedly uncover more secrets about the universe's past, present, and future. The Shapley Supercluster is not just a collection of galaxies. It is a living, breathing entity in the grand expanse of the universe, shaping the destiny of galaxies across unimaginable distances. The more we learn, the more we realize just how much there is still to discover. In the grand scheme of things, the Shapley Supercluster is but one small piece of a much larger puzzle, and as we continue to explore the mysteries of the cosmos, we can be sure that this remarkable supercluster will remain a central figure in the story of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.